Hello and welcome to the Space Policy and History Forum. I'm Teasel Muir-Harmony. I'm a curator of the Apollo collection at the Smithsonian National Air and Space Museum and a co-organizer of this forum with Bhavya Lal, who I'll introduce in a moment, and as well as the NASA History Office. And this is the 10th year of the forum, and it's our first fully virtual event. Thank you for joining us. For those of you who are new, the Space Policy and History Forum was founded out of an interest in exploring how history can inform policy discussions and to bring the space history and space policy communities together. And today's panel on the history and politics of space junk will do just that. And it'll focus in particular on the question of how and if the history of orbital debris can help us achieve a safe and sustainable future in space. If you have any questions during the event, please submit them to the NASA History Office's Twitter and Facebook accounts, and we'll be keeping track of those throughout the event. And so now I'll introduce our panel. So first up, it'll be Jonathan McDowell. He's an astrophysicist at the Harvard and Smithsonian Center for Astrophysics, and he works on the Chandra X-ray Observatory team. In addition, to his research on quasars and X-ray astronomy, he is also known for Jonathan's Space Report, an online newsletter founded in 1989 covering space activity, and for the planet4589.org website, which includes the general catalog of artificial space objects. And then we'll have Lisa Ruth Rand, who is an assistant professor of history at Caltech. And her research plumbs the intersections of the histories of science, technology, and the environment during the Cold War, with a focus on mobile waste and contingent constructions of nature and sustainability, which she'll explore in an upcoming book, I believe, titled Space Junk, An Environmental History of Waste in Orbit. And she's previously held positions at the Science History Institute, the Consortium for the History of Science, Technology, and Medicine, and the University of Wisconsin. And then we'll have Gabriel Swinney, who is an attorney advisor at the U.S. Department of State, where he handles the international space law portfolio. He is the U.S. head of delegation to the COPUS Legal Subcommittee and advises the Department of State and the U.S. National Space Council on all issues relating to international space law. He works closely with NASA on legal aspects of the Artemis program and is one of the architects of both the Artemis Accords and the recent executive order regarding space resources. And then our moderator will be Bhavya Lal, who is no stranger to the audience of this forum. And she and I have been co-hosting this series for many years now, but she has changed hats since the last time we hosted one. She is currently the senior advisor for budget and finance to the NASA administrator. In the first 100 days of the Biden administration, she was the senior most White House appointee at NASA and also was the acting chief of staff. As part of her assignment, she oversaw the agency's transition under the administration of President Biden. And before arriving at NASA, she served as a member of the Presidential Transition Agency review teams for both NASA and the Department of Defense. So thanks again for joining us. I'll turn it over to the panel now and to Jonathan to start things off.
Hello, everybody. So I'm going to give a quantitative overview of space debris and the history of space debris. If we can have the first slide. And thank you very much. This is just an overview to give you an idea of the larger kinds of space debris that we have, from nose cones to discarded rocket motors to even insulation blankets that have come off satellites. But it goes all the way down to microscopic stuff. And even a very small piece of debris whizzing around the Earth at 18,000 miles an hour is really going to hurt if it hits you. Next slide. So space debris has been with us since the very first satellite launch, along with Sputnik. Two pieces of debris went into orbit, the nose cone and the rocket stage. They've both re-entered, but space debris has been with us ever since. Next slide. So I wanted to give you a quantitative overview. There are 23,000 cataloged objects in orbit around the Earth, but the catalog is only complete even in low Earth orbit for objects that are more than about 10 centimeters in size. Smaller objects we can't track with our radars regularly, and it's very incomplete for objects orbiting the Earth at higher altitudes. So there could be as many as 1 million objects of centimeter size and even 1 billion by some estimates at millimeter size. I'm going to concentrate, though, on the cataloged objects because we know more about them. And of that 23,000 objects, about 4,500 or so are live working satellites, and everything else is junk. And so there are 3,000 dead satellites still whizzing around the Earth, about almost 2,000 old rocket stages, a comparable number of what I call litter, which are things deliberately ejected from satellites like nose cones and lens covers and things like that. And then by far the largest category is what I call disintegration debris, almost 12,000 cataloged objects that come from rockets with leftover fuel that blew up, military weapons tests, accidental collisions between satellites, battery explosions, and a host of other reasons. Next slide. So the first ever big space debris event was all the way back in 1961. A rocket stage called Abelstar 008 blew up into over 300 pieces. And almost 200 of those pieces are still in orbit today, 60 years later. And you see on the plot here, this is height versus time on the top right. Every now and again at solar maximum, a whole bunch of the lower orbit pieces re-enter, but the higher orbit pieces just keep on going. They've been up there for 60 years. Moving on to the next slide. And so just to take you through some of the important historical milestones in the history of orbital debris around the Earth. After that Abelstar explosion, the next really important event was called Project Westford, but Lisa's going to talk about that, so I won't spoil it. Then the first military weapons test that left a significant amount of debris in orbit was in 1968, a Soviet anti-satellite test. In the 70s, there were more exploding rocket stages, and there were enough of them that it really pushed people to design their rockets differently to allow the engines to restart so that you could use up leftover fuel rather than leave these things like ticking time bombs in orbit around the Earth where they might blow up years later. At the end of the 70s, we saw major reentry events crashing on Earth, particularly the Skylab Reentry in 1979, and that pushed the community around the world to design large payloads to come back down under control instead of just leaving them to re-enter randomly. In the 1980s, we saw a new source of debris, battery explosions, as well as more rocket stage breakups, notably a Russian rocket stage called Soz, a little auxiliary motor, of which about 50 of them have now blown up in high orbits, leaving a lot of debris in very high orbits. And then, more recently, in 2007 and 2009, the worst debris events we've had. A Chinese anti-satellite test, and the accidental collision of 2 communication satellites, Iridium 33 and Cosmos 2251. Next slide. And so what I'm showing here is that evolution graphically, and the different colors of these different kinds of debris, live satellites, dead ones, rocket stages, littering, and debris, of which the biggest is the green swath here, which is the accidental debris. But I want to draw your attention to really 5 historical phases in the evolution of the cataloged orbital population. Steady growth from Sputnik up to 2006, and almost overnight 50% jump in the amount of cataloged debris due to these 2 last debris events that I mentioned. What I call the CubeSat revolution in 2013, with lots of small active satellites joining the orbital population. And just in the last couple of years, the rise of the mega constellations with the launch principally of the Starlink satellites. And the slope of this curve you see now is just going so steep that the amount of cataloged objects in orbit, it's becoming really hard for the tracking agencies to keep up. Next slide. But I want to focus in on something that hasn't been talked as much about, which is I want to talk about low Earth orbit and argue that you really need to think differently about what I call lower and upper low Earth orbit. So we talk about LEO, low Earth orbit, and that's from 200 to 2,000 kilometers. But I'm going to put a boundary in the middle at 600 kilometers and tell you that upper LEO above 600 kilometers is really different from lower LEO. So let's look at upper LEO first. And I'm dividing that into two pieces, the small things and the big things. And so on the left, I'm showing just for the last 15 years, I'm going to focus on the last 15 years. And for the small debris, since that big jump in 2007, 2009, things have actually been pretty stable. And even for the large objects on the right, there's been a slow increase, but nothing dramatic, in the amount of stuff cataloged in orbit. And the other thing you notice is that the live satellites, ones that can change their orbit in red, ones that can't change their orbit in pink, are a very small fraction of the total amount of cataloged objects in this upper LEO range. So in this upper LEO range, mostly debris, largely stable, live satellites slowly increasing. Lower LEO, totally different story. Next slide. In lower LEO, there has been transformative change in the past 5 years. In 2010, it was still dominated by small debris. But today, in small objects less than 100 kilograms, it's completely dominated by the CubeSats. And this pink swath here is satellites that are working but don't have the ability to change their own orbit. So from the point of view of other space traffic, they're just space junk, even if you don't tell that to their owners. So that's totally dominated by CubeSats in the small debris population. And then if you look at the objects greater than 100 kilograms, it's overwhelmingly dominated just in the past couple of years by the deployment of thousands of satellites in the Starlink constellation that SpaceX is building. And even without Starlink, other live satellites are dominating. And so lower LEO is dominated by live satellites, not by debris, in terms of the tracked orbit population. And it's rapidly changing. Next slide. And so the summary of what I've just told you is that orbital debris is an endemic issue in Earth orbit, and it's been growing steadily since Sputnik, but it's growing really fast now. The mass is dominated by dead satellites and dead rockets. The number is dominated by disintegration debris. And in upper LEO above 600 kilometers, we see stable, slow growth. In lower LEO, we see transformative change just in the past few years. I didn't show the slide for high orbit, but the big thing for me in high orbit is we have a worrying lack of data, which hopefully is starting to get fixed, but we don't know how much small debris there is really in high orbit. And the other big worry is large uncontrolled reentries. Since Skylab, that's mostly been avoided, except for this one Chinese rocket, the Long March 5B, that has been doing uncontrolled reentries over the past couple of years. So thank you, and I'll pass control back to Bhavya and then to Lisa.
Thank you, Jonathan. That was incredible. In fact, one of my big takeaways from this discussion was how incredibly complicated this domain is and how there are no sort of silver bullets. Before we go on to Lisa Ruth, I want to ask two quick questions. One is from Facebook. Paula Siobhan-Rizig asks, how often is ISS hit by debris? Do you have any idea? You're muted.
How often is ISS hit by debris?
Yeah.
It's hit by small debris, probably I'm guessing once every year at least, because they keep finding little dings in things like the solar panels and the airlock and so on. But it hasn't really been hit by large debris that would cause serious damage. But they do have occasional, every couple of years, the astronauts have to rush into the Soyuz just in case they're about to get hit when there's a close approach. And one of the problems is our uncertainty in where satellites are is big enough that we have a lot of false alarms. And that's a real operational burden on space operators.
Thank you. So one question I have from me before we hand off to Lisa. We have 500,000, if I remember correctly, pieces bigger than a centimeter, about marble, right? Who does this debris belong to?
Yeah, that we don't know so much about. The way we know about the small debris is we do statistical surveys with a deep radar that takes a sample of the population. We know that there are contributions from leaked reactor coolant from Soviet Navy nuclear reactor satellites. We know that there are contributions from the Westford satellites that Lisa Ruth will talk about. And we know that there are contributions from just paint flakes that have been spillated off other satellites from micro debris hitting them. But there's still a lot more to learn about this really small debris population.
Thank you. So with that, Lisa Ruth, on to you. Thank you. Thanks, Jonathan.
Great. Thank you, Jonathan, and thank you, Bhavya. So Jonathan did obviously a typically fantastic job of explaining or describing the past 6 decades plus of how the landscape of Earth orbit has changed over time. And so what I'd like to discuss in following up I'd like to dive a little bit further into what the political and environmental realities were that drove the rise of our current system of waste in orbit around the planet, and look a little more carefully at the roots of the current state of debris and the conversation in particular about how to manage Earth orbit. So in recent years, many space policy experts have argued that the current orbital debris environment arose thanks to ignorance at best, negligence at worst, on behalf of the United States and the Soviet space industries of the 1960s and 1970s, and that neither space industry leadership nor everyday observers like you and I really had any sense that orbital debris or space junk would ever pose a significant problem. However, broad awareness of outer space as an environment at risk really arose at a much earlier date, truly from the very beginning of the space age. Next slide, please. Now, I'd like to actually, let's see, where are we at? My second slide now. Great, okay. So here I want to refer back to Jonathan's introduction of the first pieces of orbital debris, especially the core stage of the R7 rocket that launched Sputnik 1. Some 4% of Americans reported watching this satellite move overhead. It appeared as a bright moving star against a dark sky. Anyone who's attempted to see the International Space Station crossing overhead at dawn or dusk will know what I'm talking about here. But Sputnik was about the size of a beach ball. It wouldn't really have been possible to see from the ground without any sort of specialized equipment. And by comparison, the R7 core was about 20 meters long and rigged with reflective prisms to catch sunlight. So what most Americans who saw Sputnik in the night sky were really seeing was this much larger and shinier object. And this wasn't a secret. Many American newspapers reported that this moving star was not the named satellite, but actually the rocket core. But this act of impersonation and the object itself have since been subsumed in a kind of nationwide act of collective forgetting. The object itself, this rocket core, became a kind of visual index for the so-called Sputnik moment. But really, it didn't really matter whether people on the ground were seeing Sputnik itself or a piece of a rocket body. What it was a visible confirmation that space was now a human domain, and it signified that the geopolitical world order had shifted significantly. So a piece of space junk was the first direct encounter that most people had with outer space itself as a place that humans could reach and use. And it also heralded early recognition in the following months and years that outer space was also a place that could be polluted, that it would be potentially polluted by a very small subset of humans with the resources and capital to reach it. And this discussion arose well before satellites had become as deeply ingrained in the modern global technological order as they would become. Next slide, please. In the months after Sputnik and its debris artifacts reached orbit, there was a range of early satellite forms that followed suit. Many of these early satellites did not resemble what you and I might visualize when we think about satellites today. So projects like Westford on the left consisted of a field of hundreds of millions of copper fibers diffused into one or two belts around the planet, or Project Echo, which was basically a giant inflatable mylar balloon, or a satelloon as it was called. And both were designed to be reflective, to passively transmit signals from one point on the ground to another by bouncing the signal off the body of the satellite itself. Within a few months of Sputnik's ascent, astronomers began to really raise concerns about this kind of reflective artificial object in orbit, which they argued might obscure their view of distant natural objects. Next slide, please. So as early as 1960, astronomers around the world began to raise alarm about this potential issue. And in particular, Project Westford took off as a point of both internal and public contention. Astronomers weren't concerned so much about the test version of Westford, but more about what precedent a successful test might yield for the future of the orbital environment. So should an abundance of reflective material become the norm in the satellite industry? Some astronomers were concerned, and they discussed convening a space pollution board. Some feared a catastrophe on the level of World War II might arise should those in the position to resist do nothing. And this is a conflict that might sound familiar to anyone following the more recent debate about the Starlink mega constellation. And I've shown some of these headlines here from popular presses around the world from 1963 to provide some insight into the ways that responses to this early conflict were imbued with what we might now think of as explicitly environmental politics. And this was done in response to the possibility that Earth orbit could be mismanaged by powerful governments without the consent of those living below. Next slide, please. The necessity of considering potential dangers of the environmental mismanagement of orbit also really became manifest in early instances of re-entering objects striking land. This often happened geographically and or politically very far from the state that originally launched the re-entering object. This happened when a piece of a classified American defense launch struck a cow in Cuba in 1960. In 1962, fragments of a Soviet satellite were recovered from a residential street in Wisconsin, and a piece of John Glenn's Atlas rocket was recovered from South Africa that same year. And in 1978, a nuclear-powered Soviet satellite called Cosmos 954 crash-landed into the Canadian Arctic, into a region that was represented to the rest of the world as a barren wasteland, but is and was the home of Dene and Inuit communities who were profoundly affected both by the intrusion of radioactive debris and the joint Canadian-American cleanup forces. Even as these first objects struck terra firma and were discovered, official policy at NASA at the time was still to downplay potential risk of uncontrolled reentry. And I won't have time to go into the details of this too much right now, but suffice it to say, exchanges between leadership in the American space program convey an assumption of a moral right, an explicitly moral right, to impose a certain amount of risk upon the general public of the world in exchange for providing modern technological services supported by satellites. Now, it's worth noting that the majority of debris fragments recovered from land have been recovered in regions of the global south and the poles, which begs the question, in cases like Cosmos 954, who benefited most from the operation of the original satellite and who bore the most risk in its decay? Next slide, please. I also briefly want to stress the role of outer space itself as a natural geophysical environment in the history of space technology, from influencing the design of satellites to shaping the paths of space junk through and from orbit. And for example, one of the most famous uncontrolled reentries was that of the American space station Skylab in 1979, as Jonathan mentioned, in which the remains of the 85-ton station were recovered from Australia. Now, the fate of Skylab really illustrates nicely the complex entanglement of natural and human forces that shaped the design and decay of artifacts in orbit. So in the design stages of Skylab, engineers studied the potential threats of an uncontrolled reentry to people, animals, property, environments on the ground, and came up with a range of ideas to reduce the survivability of the spacecraft upon reentry. They ultimately devised a plan to prevent uncontrolled reentry by using what was then the in-development space shuttle to maneuver the station. However, delays to the shuttle program, alongside a particularly strong solar maximum, intervened, and Skylab came plummeting to Earth earlier than expected. with where and when it landed largely dependent on the whims of non-human forces in orbit. So in space, as on Earth, sometimes nature resists best laid plans. So testing and predictions help, but cannot account for all contingencies. And when things go wrong in space, it's often extremely difficult to clean up after ourselves. Next slide, please. So to wrap up quickly, I just want to conclude by remarking that early efforts to raise awareness of environmental risk in outer space did yield some concrete changes to the ways that spacefaring states operated in orbit. So for example, the Outer Space Treaty of 1967 calls for international consultation before the launch of any potentially damaging space projects, the enforceability of this being questionable. But it also spurred provocative acts of resistance by nations at the periphery of the Cold War space race that perhaps we might be able to touch on in the discussion part of today's event. And I'd like to end here with an invitation to consider how the longer history of decay in space and also these early encounters with both real and anticipated mismanagement of orbit could potentially inform which voices might be brought to the table now as the international policy community considers how best to address this truly global environmental issue. Thank you.
Thank you, Lisa Ruth. That was fascinating. I did not know we tried to launch millions of copper needles in space. And I guess luckily they all clumped together and made it easier for us to track them. One quick question for you before we move on to Gabriel. You mentioned that Skylab was 85 tons. Did the entire 85 tons come down as a single chunk, or did it break up into little pieces?
That's a great question. Thank you. It did break up into pieces, but some massive chunks of it did survive and were recovered in parts of Western Australia. There's a pretty amazing picture of part of that, a large fragment actually being a guest of honor at the Miss Universe pageant in Perth that same year, in which all these beauty queens are gathering around a large, what appears to be a fuel tank, I believe. I could be wrong. Actually, no, it was an oxygen tank, I believe, from Skylab. So certain massive parts of the station did survive and fall into pieces into Western Australia, but a lot of it did burn up in the atmosphere during reentry. Some of the less massive fragments did burn up, as many reentering objects do.
And we know that there was this Chinese rocket body that reentered recently, uncontrolled reentry. Have there been others between sort of Skylab in '79 till the Chinese one today or this year?
That is something that I think Jonathan is probably more equipped to discuss. I know that he has a lot of thoughts on this particular question about uncontrolled versus or intentional uncontrolled versus unintentional controlled reentries. Jonathan, did you want to speak to that?
Sure. Yeah. I mean, so after Skylab, there were a couple of 10-ton rocket bodies that re-entered in the 80s. But since the mid 80s, the only uncontrolled re-entries that weren't accidents have been these two Chinese rocket stages that re-entered in 2020 and 2021 that are 21 tons each. We did have Salyut 7 crash into Argentina in '91 and Phobos Grunt crash into the ocean, I think, in 2013. But those were things that weren't meant to re-enter. They went wrong. So we've been very careful, with the exception of this Long March 5B. We've been very careful since Skylab not to have that happen.
Thank
Of course,
you.
we also have, I do want to mention also Tiangong 1's re-entry a couple of years ago, just because I happened to be living in Wisconsin at the time, which has its own history of survived fragments striking terra firma. And there was a lot of concern at the time that the fragment of the Chinese space station would hit ground. But as Jonathan has said online many times, usually this is definitely not going to happen. Don't worry about it. But this large public outcry about re-entering objects and not knowing where they're going to land is definitely an issue of perennial concern, I think, in a broader popular sense.
Thank you. I remember reading somewhere that this Western Australia town that had the Skylab landing, they tried to fine the United States for a littering fee, a few $100s, I think. And I think a few years later, a DJ in California collected money from his listeners and sent the littering fee to Australia. So, we delivered.
That's correct. It was $400, and now there is a paid in full sign up in the museum in Esperance where the Skylab exhibit is on display.
That's awesome. Okay, well, with that fun anecdote, Gabriel, turning it over to you. You are a lawyer, which means you will make it difficult for us to understand stuff. So go.
Thanks. I'll try not to do that. I think mine may be actually the least technical of all the presentations today, perhaps. So could we pull my slides up, please? Maybe we can make that full screen. Yeah, there we go. All right, let's go ahead and pop to slide number 2. So I'm going to talk about sort of the legal and then transition into the policy sort of background for this in terms of where we are now, and then what are the possible solutions for the future. And I'll touch on the history as well. And as you said, I am a space lawyer, so I'll start with that. And you know, one of the main questions I get asked when we talk about debris, whether it's re-entering debris or debris that's in orbit, is what does space law say about it? In particular, what does the Outer Space Treaty that was negotiated in 1967, what does it say about space debris? And the short answer is nothing. If you look in the Outer Space Treaty, if you look at some of the other international conventions about outer space, there are no provisions specifically addressing space debris. So we can talk more during the comments if we want about sort of why that is. I think Ruth has already touched on some of those a little bit. Some of that was intentional. But for better or worse, there's nothing directly on point. So what we are left with are the provisions in space law that sort of get at these issues sideways, you might think about. And in particular, there's 2 concepts that are in the Outer Space Treaty. They're both in the same article, Article 9, if you want to look it up yourself, that are potentially relevant to space debris. The first one is due regard. And what that means is that every country that launches spacecraft, and I should say here, this holds whether you're doing it yourself, say through a space agency or a Ministry of Defense, or whether your own private commercial actors are doing it. It's the same rules. You have to give due regard to the corresponding interests of other countries in outer space. That's it. That's that obligation. Now, what that means is entirely up for debate and discussion. But at the very least, it could mean something like you should take into account, you know, the impact of debris you might generate, either through normal operations or anticipatable mishaps. So that's one potential legal hook to think about debris. Another obligation is more specifically about harmful contamination, and signatories to the Outer Space Treaty are supposed to avoid harmful contamination of celestial bodies in outer space. So some people look at this and say, well, see right there, there's sort of an environmental law or an environmental consciousness concept in space law. And that's certainly one possible reading of the treaty. I should say that historically, not only the United States, but other spacefaring countries have read this provision much more narrowly in terms of preventing, let's say, biological contamination of Mars, for example, really having to do with maintaining the purity of the science that we can conduct there. And it hasn't really been used to think through debris problems, but at least that idea is potentially out there. And then the only other thing we really have in space law in terms of the real black letter law is liability, right? How you respond to an incident that might happen sort of after the fact. And there's really two rules. They're quite simple to write down and then very hard to apply. If you have damage that occurs in outer space, you have to pay if you are at fault. It's fault-based liability. Now, what fault means, who decides, all of those are open questions. In particular, what counts as fault is a real remaining question in space law. So that's the rule in outer space. If you cause damage on the ground or to aircraft in flight, it's actually a lot simpler. You have to pay. If you're a country that launched, if you're what's called a launching state, and your object causes damage to aircraft or something on the ground, you automatically have to pay if the harmed country asked you to. So that rule, at least, is quite straightforward. Next slide, please. So as Jonathan and Ruth have mentioned, there have been a number of high-profile incidents. Instead of talking about the debris generated, I want to briefly talk about the international response to some of these. The first is the Chinese anti-satellite test in 2007. All right, this was at a relatively high altitude, as you saw from Jonathan's slides in particular, and generated a large amount of persistent space debris in low Earth orbit across a wide range of altitudes. So there was pretty significant international outcry, right? A significant criticism of the Chinese government and the actions, and some of that criticism was couched in terms of outer space treaty obligations and whether or not the Chinese government was complying with them. There was, of course, Operation Burnt Frost by the United States military in 2008, which was the destruction of a satellite that was already re-entering. It was relatively low in altitude at the time it was destroyed. My understanding is that it didn't generate significant long-lived debris. So there's one potential distinction there. And at least at the time, the United States articulated the reason in terms of public safety because of, I think it was hydrazine fuel, which is highly toxic, that was remaining on board, and the desire to destroy that so it would disperse in the atmosphere before it reached the ground. What you can see, the picture on this slide is actually that satellite being destroyed. It's a telescope image of the destruction of that satellite. Then, of course, as Jonathan mentioned, we have the Iridium Cosmos collision in 2009. We've already talked about that. Interestingly, the liability provisions of the Liability Convention and the Outer Space Treaty were not used or not invoked in that collision for some complicated reasons, basically having to do with both parties probably being at fault and then no one willing to say you were more at fault than me. So they sort of walked away and resolved it through diplomatic channels. And then most recently was Mission Shakti, which was an Indian anti-satellite test in 2019. This kind of falls in between the Chinese ASAT test and Operation Burnt Frost in terms of altitude. And then as a result, falls in between those in terms of the amount of space debris generated as well. One interesting thing I think about that is because it's the most recent, perhaps because it's sort of the most modern ASAT test, you saw the Indian government do a number of operational things in this mission that appear to have been designed to reduce the amount of space debris. Right? It was at a relatively low altitude, but also the impacting vehicle, so the test weapon system, came in from above, and so directed much of the energy into the target vehicle, sort of downwards towards the Earth. So it appears at least that the Indian government did this with a consciousness of trying to minimize generated space debris. Next slide, please. Okay, so we all know what the problem is. I'm not going to go over that again. It's already been described really well, right? We've got a lot of human-caused stuff in LEO. I should say we haven't talked about geostationary orbit, but there is at least a potential concern about geostationary orbit as well because of the sort of physical constraints of that orbit. I want to focus instead on the bottom right-hand corner of this slide. What are our responses, right? What are the possible responses to the problems of space debris? And maybe this can transition us into the conversation here. I really see at least three buckets of responses. One, as with any problem you might have in life, you can live with it, right? And living with it is essentially what we're doing right now. Just recognizing that space debris will be generated and not trying significantly to minimize it, at least in a way that doesn't impact your operations. Now, there are ways to reduce the dangers of that through things like space situational awareness, SSA, space traffic management, STM. A huge amount of resources are put into this, particularly from the United States government, but certainly others as well, to track objects and make sure that people are maneuvering or space objects aren't having close conjunctions, things like that. So that's sort of the living with it response. Query whether that's sustainable over time, given the rapid uptick in numbers that Jonathan highlighted in his slides. The next bucket of possible responses, of course, is prevent it in the first place, right? Prevent the creation of space debris before it happens. So let's go to the next slide and dig into that. Next slide. Great. So even once you're in the prevention category, now there's a lot of words on here and I'm not going to go over them all, but once you're in the prevention category, even there's sort of two ways of thinking about prevention. One is forward-looking, preventing preventing the generation of space debris before it even happens, right? Before you even get off the drawing board. You can do that by creating rules, either internationally and domestically. Many countries, including the United States, do have some rules that they apply to their own launchers and space operators about the generation of debris. You could try to draw from those parts of the Outer Space Treaty that I talked about earlier, and you might try to define some best practices, right? Things that aren't legally binding rules, but are best practices, like there's some UN guidelines on orbital debris, for example, and you can sort of try to build those into your operations approach. The benefits of this approach, right, are sort of obvious, I think. If you can pull it off, legally binding rules are pretty clear. They can have penalties associated with them. But on the other hand, you have sort of a first actor problem here. Right? This is a standard collective action problem where most countries, most launching states, don't want to place significant restrictions on their own actors or their own operations if no one else is doing that too, right? No one wants to tie their own hands if their potential commercial competitors or strategic competitors aren't doing the same thing. So you have a little bit of a, touching nose situation where no one's willing to go first. The other way of dealing with prevention is what I like to think of as a backwards looking way of dealing with it, which is really all about deterrence. Right? And that's where I talked about liability. Right? If you generate space debris and it crashes into someone else's stuff and you have to pay hundreds of millions of dollars, well, that might deter other people from generating space debris in the future. But there's all kinds of unanswered questions there. Like I said, what counts as fault? There may well be lots of kinds of quote unquote normal operations that are still dangerous, right? That wouldn't count as fault, but that still impose a danger or risk on the broader community. And then there's an open question as to whether countries will actually use a fault-based system or a liability-based system to respond to this. As I said, for various reasons, it hasn't actually happened yet. And then, of course, those costs, just like anything with regards to liability or insurance or whatever, those costs will ultimately get passed on to someone, whether it's operators or national governments. Okay, so let's go to the next slide. And look at the final bucket of potential solutions, and that's cleanup. Right, and this sort of touches on all the range of problems you can have in space. Right, there's technical problems with cleanup. How do you do it? It's going to be very, very expensive in terms of propellant, in terms of operational costs. As you've heard from two previous speakers, there's a huge range of debris. You have big things, you have little things, you have some that are, sort of quasi-frozen droplets. You have little threads, pieces of paint. Right? So you have to sort of pick your priorities, and I'm not sure it's entirely known, actually, what are the priorities. Then you also have legal issues, right? Every single piece of space junk is owned by someone. Whether we know whose it is or not, the Outer Space Treaty is very clear that you own your space objects, including the component parts, including debris that's generated by them, forever in outer space. So one can't just go up and clean up someone else's space junk, at least not without permission. And whether you could get that permission and sort of how those questions would work is still very much to be determined. And then what if there's an unintended consequence? What if, for example, you get permission from another country to deorbit one of their large upper stage bodies, but something goes wrong and it ends up causing damage to a third party? Who's responsible for that? These are serious questions that could well deter anyone engaging in significant cleanup operations. And then finally, of course, there's the business case. Someone's going to have to pay for this. It's going to cost a lot. And it's not something that companies, at least, are going to undertake sort of on their own dime. Probably the same goes for national governments as well. It's another one of those collective action problems, right, where you don't want to just help the whole community, the whole world, while taking on the entire cost yourself. So I'll end there. That's a bunch of problems. I don't have a whole lot of solutions, but at least we know where to start. So thanks.
Thank you, Gabriel. Before we go on to the question session, and we've gotten tons of questions from social media, thanks to Kat's great work compiling everything. But before we go on to that, Gabriel, a question. On your first slide, you had mentioned the Outer Space Treaty having, a liability clause. And earlier, Lisa Ruth had mentioned a nuclear reactor that fell over and dispersed radioactivity over Canada. Was this liability clause invoked, and how did that go?
Lisa, Ruth may have more details than I do. My understanding is that that dispute was resolved through diplomatic channels, and that so in other words, the Canadian government and the Russian government spoke sort of through their embassies and through their diplomats and came to an arrangement that satisfied them both, which means that sort of no one worked through the actual steps and stages that are set out in the Liability Convention. So there's not really any practice there. It's all behind the scenes. But Lisa, Ruth, you have more information there than I do.
So that's an interesting. You're making me think back on it and what counts as working behind back channels or explicitly with the Liability Convention. So, for example, I know that the Canadian government filed a claim with the Soviet government within the statute of limitations, right, within the 1 year required to do so legally based on the convention. And I think, but it was definitely settled to, I wouldn't say to the satisfaction of all parties, because the Canadian government filed for over $6 million. The price tag actually came to over $14 million, and the Soviet Union relinquished a tidy sum of $3 million. So it was definitely I wouldn't say it was totally mutually agreeable, but everyone did agree upon it eventually. And I did want to briefly mention, since we're talking about Cosmos 954, I think, Gabriel, what you mentioned about the complexity of defining fault is really important. But in the case of instances like Cosmos 954, also it plays an issue of what counts as damage that can be compensated, whether through the convention itself or through diplomatic back channels. There's a lot of complexity in interpreting value and liability, even with these more explicitly codified structures in place.
So you're saying the system worked, sort of?
It sort of worked. They moved on, right? But this is like the easiest possible case, and I think that's indicative, right? This is damage on the ground. There's not a lot of actors involved when you're talking about the damage in Canada. I mean, there's lots of people who are affected on the ground, but you're not talking about 4 or 5 objects colliding in like a chain of collisions in outer space. And so you're dealing with strict liability on the grounds. The legal questions are at least reduced. So the fact that dispute was sort of squished through by the international community and like sort of managed to get past it, I think just suggests that anything even remotely more complicated is going to just be orders of magnitude more difficult to deal with, particularly in terms of on-orbit collisions. Because then you really do need to sort of think through, like, who did something wrong, or did anyone do anything wrong? And then what does that mean for all future operations, right? Once you've decided on a standard, what counts as fault, well, oh my gosh, what if you look and it turns out everyone's doing that, or 20% of operators are doing that thing or behaving in that way? Now they're all potentially at fault. So none of those problems have had to be addressed yet. So yeah, they got through it, kind of. But that doesn't help us a whole lot for the future.
Okay, well, that's good to know. Okay, so thank you, everybody. That was incredible. I learned so much, and I'm sure all the people who have joined have learned as well. I want to open it up to questions, and also, Teasel, my co-host, Stephen Garber, NASA History Office, Brian Odom, NASA History Office. If you guys have any questions, feel free to shoot them to me or ask yourself. But I want to start actually with the one little piece that Gabriel mentioned, and it's a question for Jonathan. So Jonathan, tell us why debris matters. And let me give you the analogy. Like, we have boulders in forests. We don't care, right? We only care about boulders if they are on highways. And we're afraid of collisions, right? So the question is, what % of the debris that we have in space will lead to collisions that will affect our ability to operate satellites, right? It doesn't matter if it's 1 million pieces, 10 million pieces, if they're all in tiny little corners that don't affect our satellites, it doesn't matter.
Right, but that's not the way space works. In space, all the objects are going at 18,000 miles an hour in every direction all at once. There are pretty much no lanes, and so you have constantly right now we have sort of false alarm warnings as objects are going to come, some random object is going to come within, a few miles of your satellite. And so there are close misses, dozens of close misses every day. And we're really just, it's not like the boulder occasionally falling down the road. It's like walking across a World War I battlefield with everyone shooting at you, and you're just hoping the bullets don't hit you. And yes, it's the probability of being hit is low enough that we haven't had any collisions in 10 years, but it's a close thing, and we're going to run out of luck eventually.
Got it. So the short answer is that most of that debris matters. We can't just be worrying about some percent. Although I know there's probably knowing this crowd, I know the answer is complicated. So let's wait on that a little bit. I want to turn to Lisa, Ruth, a bit and talk about it is some history, but also a different domain. So to what extent do you think the orbital debris challenge is analogous to the climate change, the GHG warming issue? And then of course the follow-up is if they're analogous, what lessons can we learn from the climate change debate?
That's a great question. I will say that in a rhetorical sense, they are directly analogous. So in 2011, the National Research Council put out a report stating that the orbital debris environment had reached a tipping point, which is a term that's directly borrowed from climate change science and politics. It's one that suggests that we've crossed a threshold beyond which there is no, we've crossed the point of no return, basically. And there's a lot there's a reason for that, right? So one of the main arguments about how to kind of raise awareness of climate change is that sometimes it's hard to see it happening in real time, right? We can see effects of it in superstorms, in different, in heat waves, in droughts, in sea level rising, but the difference with space is that, you don't, I should say, with climate change, there's also certain charismatic indicators, like, for example, a polar bear on a floating, cut off on an ice floe, right? That can trigger a kind of emotional response to this broader problem that's harder to visualize. There is no charismatic polar bear for outer space, at least not yet. But there's a similar kind of issue of this broader global problem being one that's difficult to draw connections to in a broader sense, I should say, in kind of that same emotional sense. But on the level of in terms of measuring the problem and responding to it, I will say I do want to note that climate change and orbital debris are not distinct problems in some senses. So, for example, a study came out about 2012 by a group of chemists that suggested that the self-cleaning mechanism of orbit, so this periodic expansion and contraction of the exosphere that draws in uncontrolled objects at lower orbits, that kind of really cleans up after our messes for us. It's a very fortunate natural reality that we have in place. That's becoming less efficient thanks to climate change, that the exosphere is contracting. And so that self-cleaning mechanism isn't as efficient as it once was. So I just want to note that those are not two necessarily distinct issues, but also I would say that in terms of what lessons we can learn from each, I always like to point out the Montreal Protocol as an example of from recent history of an instance where a global environmental issue is identified, a problem is identified, and solutions are put into place, and the situation started to be reversed within a decade, which is really unusual. And it happened, during a period of low regulation, a period of high conservatism around the world. It's during the Reagan era, the Thatcher era, and yet this is the issue of I should make sure I'm clear. This is the issue of the depression in the ozone layer. So from identification that the depression was happening, the scientific mechanism behind it, to starting to reduce the use of CFCs really happened very, very quickly. And that was a combination of factors ranging from it being of personal interest to leaders like Reagan and Thatcher. Reagan, who'd experienced skin cancer several times. Thatcher, who was a bench chemist before going into politics. Also, the ability to provide visualizations, real-time visualizations using satellites of the Depression as it worsened, as it got better, but also just largely this combination of these different factors led to, and also I should say a distinct solution, right? The reduction of CFCs, all combined together to make this strange incident of a global environmental problem being something that could be addressed in short order, and actually had the political purchase to do so. I don't know, right, how that would work necessarily for outer space, but it's one that I always like to point to as a unique incident of success that we might look at for examples.
Yeah, so I think what you're saying is we need to do a deeper dive case study of the Montreal Protocol to see what specific lessons we need to pull out, which lessons apply. So that's a good homework assignment for us. Thank you. I see Stephen Garber has put something in our chat, and he's noticing that, Lisa, you've made an excellent point about it being difficult to notice orbital debris in real time. This connects to the tragedy of the commons. Oops. Where if drop a banana peel on the sidewalk near my house, it's more likely then someone will slip on it than I personally will slip on it. So that's a good point. Thank you. And then Lisa, Ruth's response is potentially, except there is no space junk cancer. So we need to think about that a bit. So moving to the next question, Dragonship 10 wants to ask Jonathan, and I agree with Dragonship 10. So because it relates to the question I was getting to earlier, what is the most dangerous debris in terms of size? And then I guess, what do we do about that? So Jonathan, if you can hit what's the most dangerous debris, and maybe make a distinction between small and large debris, and comment on that.
Right, and Bhavya, you and I have talked in the past about the issue of small versus large debris. If you are a satellite operator, you're most likely to be hit by a small piece of debris just because there's more of it. But the large debris is in some sense the most dangerous, because if two large objects hit each other, like the Iridium Cosmos collision, they increase the total amount of debris so much. And so in my view, the top priority is to get rid of some of these large pieces of debris in long-lived orbits. And that's what brings down the probability of sort of runaway collisions. And so there are a bunch of old Soviet rocket stages from the 80s that are about 5 to 10 tons. There are a few large dead satellites like Europe's Envisat that's in the 10-ton range. Hubble itself, even though it's still working, right? Hubble's a 10-ton satellite without the ability to maneuver. And so eventually we've got to bring it down. And so I would say there's a few, maybe of order 100 large objects that should be at the top of your space garbage collector list.
Okay, and I understand we do have space garbage collectors in our community, so we'll get right on it. But actually, that brings me to a question for Gabriel. You mentioned the top most egregious list, and I have looked at least the top 50 list, and there are no U.S. objects on the top 50 list. It's mostly Russian, and then the Envisat from ESA, and then maybe a few Chinese ones. So Gabriel, the question for you is, what do we do if these objects don't belong to us? How do we bring them down? How do we persuade our fellow countries to do the right thing?
Yeah, it's a great question, and I think it's worth noting. I think you mentioned in my introduction that I spend a lot of my life in Vienna at the UN Committee on the Peaceful Uses of Outer Space, UN COCUS, which, for those who don't know, is sort of where the international community comes together to talk about international space law and policy and technical things. And every single time the issue of space debris comes up, some of the countries you mentioned that are the generators of some of the largest bodies of space junk make very long statements reiterating their continued ownership over those objects. That is a firmly held position by some of those other governments. It's been consistent for decades, and it's a real problem, as you say, because it means that if someone else wanted to remove those objects, you'd be infringing on their own property. How do you do that? I think one way is to lead by example, right? There's the Hubble. There are a few large-ish US-owned objects or European objects, right? You can imagine a collaborative mission between the United States, ESA, JAXA, sort of like-minded partners to do some test cases, right? This is sort of my own personal hope, is that we'll see over the next few years some test cases where space agencies, countries, private actors will work together to deorbit or transfer to graveyard orbits some large objects that are intentionally international to kind of work through those problems. But the political and fiscal, frankly, will has to be there. Or we can do these things, particularly for large objects. It's not technically impossible, it's just expensive. So what I would say is you start with the easy stuff, right? You start with the easy stuff in terms of the politics, right? American company removing a European satellite, something like that, or vice versa, whatever. That's relatively easy politically. You work it through and you make a big to-do out of it. You get good press, you get good tweets about it. Really, that's how policy can change. And then you start shopping that idea around to the rest of the international community. It's also important to make it clear that there's a distinction between cleanup and between espionage or salvage or something that might be seen as more nefarious, right? I think there is a concern in some countries' minds that if you can deorbit an object, you can also inspect that object, or you can inspect other objects. And while that may technically be true, sometimes, depending on your technology, I think it's going to be absolutely critical to keep like a serious firewall between those operations, so that there's no suspicion that your cleanup operations are actually a cover for something nefarious. If you're going to clean something up, you really just need to deorbit it or stick it in a graveyard orbit, right? Don't futz around with it. Don't look inside it. All of that stuff is going to have to develop over time and sort of build confidence. So there's no quick and easy answer. You're just going to have to do it. Start with the low-hanging fruit and build yourself up from there.
That's good advice. Thank you. So the top 50 we know rocket bodies, or the top 50 most egregious are primarily Russian and other countries. Jonathan, I tried to kind of dig at this a little bit earlier. Can you say more about which are the countries which have the most debris up there, or the most objects, not even debris?
Yes, and it's really independent of either objects or debris or large things or small things. The answer is most of the stuff that's currently up there is Russian or American. And then a close third now is China, but most of China's stuff is the debris from that one ASAT test. And then everyone else is currently far behind. So it's really largely a Russian and American issue in that sense.
So that's a really good point, Jonathan, in that, and again, going back to the climate debate, the problem was created by a smaller number of industrialized countries, and now we're asking, some of these developing countries that they need to be spending money to do the right thing. And to some extent, when we ask for more regulation or more technology, for example, to ensure that we don't create more debris, we are adding a cost. How do we address that issue? And again, this is a question for any of you who want to take it. And in other words, how do we encourage responsible behavior by other countries when they don't see themselves as having created the problem?
Yeah, well, I think Gabe's absolutely right that it's you set the example. And I do think that, it ought to be so can we get rid of the Russian rocket stages? I know they're at the top of the list, but like I said, I think, Hubble and Embosat are up there too, depending on how you do the metric. So it's not just them. Take a few down, work with the Russians to do a joint example, invest in getting the top 10 removed, and then I think it becomes a much more internationally even playing field once you've done that.
Got it.
Yeah, I'll speak to that too a little bit. And so in addition to the the sort of active debris removal question, which I do think is important. And I should say, just to follow on to my own comments before, I don't want to imply that Russia is like the only negative actor here. The United States is a huge contributor, particularly on the small sat side, of course, right? And if I had to pick a space agency to go and grab an object in outer space, there's a pretty good chance I'd pick Roscosmos. If you read some of the old school stuff those guys used to get up to in the 80s and 90s, if anybody can slap together something to deorbit a satellite, it's probably Roscosmos and the cosmonauts. But in terms of actual regulation, you mentioned that, and how do we avoid imposing costs on sort of emerging space actors? And that's not just developing countries, right? That can also be educational institutions. It can be startups. It can be anyone who is sort of operating on a reduced budget or technical abilities. And you're absolutely right that as we increase things like even non-binding guidelines that I talked about before, even sort of best practices, those do impose costs. Jonathan's slide showed how few small sats are maneuverable. That's partly because of size constraints and mass constraints, but it's also because of cost constraints. There's an increasing number of small size, small power propulsion systems that are available, but those are expensive and they're hard to do. So I think it is possible, though, to develop intelligent regulations. Right? So, for example, and I'm just sort of spitballing numbers here, but you could imagine countries putting in place rules that are particularly stringent if you're going to be launching a mega constellation, right? If you're launching 1,000 satellites, they've got to be maneuverable, they've got to be trackable, a whole series of technical things. They have to deorbit after a certain period of time. But if you're an educational institution, you're only launching, say, 5 or fewer satellites, then maybe you have a different set of rules. Or if maybe you're only launching to a certain altitude, right? 200 kilometers and below, you can do whatever you want. Again, I'm just making these numbers up. But it doesn't have to be, and it probably shouldn't be, one set of rules for every regime and one set of rules for every type of actor. This is, this is what policymakers are supposed to do, is to make intelligent distinctions. And I do think it's possible to do those in a way that that's rational and that doesn't impose too much undue cost on developing actors who can be developing countries or emerging space actors on the commercial side.
Your optimism is appreciated, Gabriel. Turning to Lisa Ruth again for a moment. Gabriel had this whole list of sort of prevention before and after. Putting on your history hat, have we had any approaches to mitigation in the past? And are there any lessons from the past that we could be learning? And again, I'm talking not about other domains, but in the space sector. Have we ever tried to do it? Or is it or is an interest in orbital debris mitigation and remediation something that's kind of more recent?
Well, I think actually I was thinking of bringing this up at the tail end of the last question because I think Gabriel brought up a really good point about these kind of more intelligent ways of trying to model and enforce better behavior in terms of mitigation. I think, and I brought up Project Westford in the talk, but since it was such a brief set of remarks, I didn't really get to go into too much detail. But that's actually a very early and a very good, I think, example of an instance where the shape of a project was shifted in response to feedback by a specialist group. So in this case, Project Westford, which was a Department of Defense project, sought study by external astronomers. They were kind of given the burden of proof to suggest whether or not the project would be safe in its current form. And astronomers demanded certain changes to the payload to make sure that these dipoles would not be long-lived, that they would re-enter within a matter of years, would not be permanent, that any potential unforeseen circumstances would be short-lived and non-permanent, that this particular system would not be highly survivable. So or rather I should say that implies something about reentry, which is not quite relevant here. So in that case, particularly following this kind of large public outcry, there were changes made to the project to accommodate the requests of this particular specialist community, this international specialist community. And the reason why I think it's also important to bring up to highlight a lot of these incredible similarities between Westford and Starlink today is that we have very different power actors in play here. We had, in the case of Westford, it was a publicly funded project conducted under the auspices of the Department of Defense, but still taxpayer money. And with this public uproar, presumably that could have had an effect on how the DoD went forward with shaping that project, and it was again changed to make sure that the dipoles reached a resonant orbit that they would re-enter within a short period of time. That said, I also want to, of course, note that per my presentation as well, considering the non-human natural forces at play, that some of the dipoles did clump together, as you mentioned, Bhavya, and did not re-enter within a short period of time, that they're still up there and they're trackable because the surface tension brought them together and ruined their mass to area ratio, which was required to bring them down over a short period of time. So the reason I'm bringing this up is because I think what we have to look at here is also, the shifting power landscape. When you have kind of a federal government at the helm that is in some ways, and not always, but in some ways answerable to a taxpayer public, things might happen differently than they would if you're talking about a private industry that doesn't have the same kind of organizational structures and the same kind of accountability. So, I know that SpaceX, for example, has put forward some studies, has done a few test runs of trying to dampen the reflective nature of some of the Starlink satellites, but in the meantime, it's still sending up, dozens of satellites at a pop at a considerable clip, and most of those are still reflective. And there is no pause, and there is no accommodation before continuing to launch these experimental satellites. So I hope that answered your question. I think it's just an example again of the kind of complexity of these political structures, the power landscape, and the geophysical landscape all coming together to really complicate the issue of mitigation. But also we do have a good example of this working. It's just under a very different circumstance, a very different geopolitical and political circumstance in America, specifically in the early Cold War, compared to what we have today in this kind of new space age that we're in the middle of.
Yeah, agree completely. So there's a bunch of questions. I'm going to put them together in the same bucket. Olivia Lake 3, Bardi C Voice, I'm sorry if I'm butchering that, and Kai Wayne Holland have kind of the same bucket of questions, which kind of fall into, are there efforts to recycle debris? I mean, we've only talked about one option so far, right? We just assume we need to either take it up. If it's high enough, we put it in a graveyard. And if it's low enough, we deorbit it. But there's also a third option, which is to recycle it. And so that's one part of the question. The second one is, can we salvage parts of dead satellites? And what rules would govern someone claiming salvage rights over dead satellites? So I guess the question for all three of you, Lisa, if you can maybe talk from salvage in other domains, Gabriel, if you can talk about the legal aspects, and Jonathan, if you can talk about the technical aspects. I cannot imagine it's very easy to salvage parts from satellites.
I can briefly refer back to the history of salvage efforts in outer space. So in the era leading up to the space shuttle program and throughout the space shuttle program, NASA in particular attempted to take a kind of an ethos of reuse, to embrace an ethos of reuse in its approach to the satellite infrastructure. So the space shuttle itself, one of its expected uses was as a kind of a salvage truck, really. That satellites, when they break, instead of just letting them languish on orbit, that the space shuttle, alongside orbiting space station refurbishing depots, refueling sites, a network of tugs, that instead those satellites would be would be subject to the 3 R's, not reduce, reuse, recycle, but retrieve, refuel, repair. It's actually 4 R's, redeploy. So there was an effort to do so, particularly during the early 1980s, the pre-Challenger period. Several satellites, including, for example, the Hubble, were designed specifically to be refurbished, to be retrieved, because retrieving a satellite in microgravity is not something that's an easy task, and that the satellite would need to be purpose-built to do so. This attempt at refurbishing and reusing was one that saw that turned out to be not something that was durable for many reasons, which I will go into in my book. But there is a precedent for that, an effort at that, but it required ultimately a wholesale rethinking about the satellite infrastructure at all stages, not just a reusable launch vehicle, not just a reusable landing vehicle, but satellites built to be salvaged and repaired, brought back to Earth, or redeployed in space. Again, it required a much more comprehensive view of reuse.
I can give a little bit of the sort of legal policy perspective, and with some history in here too on that. You know, a lot of people online will say that space law is similar to the law of the sea or maritime law. That is not true. It is not remotely true. And one of the ways that it is the least true is with regards to the concept of salvage. Right? We're all sort of vaguely familiar with the concept of marine salvage, where if an object is abandoned, so long as it's not a sovereign vessel, right? So long as it doesn't belong to someone's Ministry of Defense or something, you can eventually salvage it, and there's different rules about that. You can get a prize fee or get to keep it or whatever. There's a whole regime, right? It's a whole thing maritime lawyers do. There is no legal salvage in space unless you're salvaging your own thing, full stop. There's no regime for it. So if you're going to be salvaging stuff, the legal answer is you're going to have to get consent, right? Whether it's for a paint chip or whether it's for a functioning satellite or whether it's for a rocket body, you need consent. Which at the moment means that every single operation is going to be a one-off in terms of policy and in terms of arrangements. If you could salvage it, and my co-panelists can talk more about the technical ability there. If you could technically salvage it, you're going to need to come up with sort of who gets to use the parts and what are they worth, and you're going to have to work all that stuff out at the same time as you work out permission. So again, even if you could solve the technical problems, there's not sort of a defined regime like you have in the law of the sea, which was very useful and designed intentionally over many decades and centuries, frankly, for the law of the sea to keep sea lanes and ports open and that kind of thing. You haven't seen that in space. And that's largely a result of the history of the negotiation of the Outer Space Treaty, right? This is Space Policy and History Forum. We have to remember that the Outer Space Treaty was negotiated in the context of the Cold War between two contentious parties, you know, the West, led by the United States, sort of the other half of the world led by the Soviet Union, and they had very different views about what space should be for. And the compromise they reached that allowed them to reach agreement on the Outer Space Treaty and sort of a modus operandi for outer space was largely what's mine is mine, what's yours is yours, and we're each going to do what we want, and we're going to recognize the other's ability to do that thing. Right, that's a wild overstatement, but that's the basic sort of principle of space law. So to get past all the problems that compromise has frankly contributed to over the decades means we're going to have to start collaborating. It means you're going to have to get countries, private actors together and start consenting to things. But we don't have an existing system like you do in the law of the sea that you can just kind of build off of.
Lisa,
Yeah.
did you want to add your comment on the Indonesian satellite? I think that's really important.
Sure. I just wanted to note that that what Gabriel said is correct, that there has to be firm consent in place. And this did happen with the salvage of the Palapa B2 satellite, which was an Indonesian satellite that failed to reach GEO, and which America retrieved using the space shuttle, and which was resold, I believe, to China. So there has been an example of salvage and reuse. But yeah, all the terms had to be very, very clearly delineated so that this wasn't an act of aggression, right? Ultimately, what it could have been if not all parties were in direct agreement about what would happen at all stages.
It would be piracy otherwise, right? Space piracy, yeah.
Yes. Oh, sorry. But yeah, putting the space pirates aside for a minute, it's worth noting it's not as international as Lisa Ruth makes it sound, in that they were both the two retrieved satellites, the Indonesian one and also a Western Union one, were both American-built satellites that had not really been handed over to their international owners, and in fact, I believe at the time of the rescue were the property of Lloyd's of London, and so that simplified things a little bit, but it does give you precedent, and yes, those satellites were relaunched and operated for many years in geostationary orbit once they reached their final orbits. So that's a successful example, but you know what? A lot of the cost of that was really kind of given for free by the space shuttle launch. And I think in most cases, trying to make an economic case for salvage, for actually bringing a satellite back down to Earth, refurbishing it, and launching it again, or reusing some of its parts and launching them again, it's really hard to see that being worthwhile from an economic point of view. And so I think, and even bringing it down to a low orbit, fixing it, that's questionable. One important development that has happened in the past couple of years is the Northrop Grumman satellite servicing. I can't remember their subsidiary name, but they've gone and had a satellite that goes up to an old geostationary satellite that's out of fuel, docks with it, and just sits there, providing fuel and orientation for an extra 10 years, and so extending the life. And so that's sort of close to salvage, and it could equally well be used to bring it to another orbit. There has been talk of going up to a satellite. There was a Pentagon plan to saw the antenna off an old satellite and stick it on a new one to reuse the expensive bit. So people are playing with this, but I'm just skeptical that it's going to be, a lot of satellites last 20 years. When was the last time you reused your 20-year-old computer? Right, and so it's more appealing usually to go to Best Buy and get a new one, and so I think it's going to be a while before that gets to be a reasonable option.
Thank you. This is a fascinating discussion. I learned a lot, but one thing I did not know at all, that we brought back a satellite that belonged to the Indonesians. Possibly, belonged to Lloyd's of London, and we sold it to China. And I guess we just have to read Lisa's book to learn more about this. So Lisa, you have to tell us what the name of this book is, so before the end of this show, so we can all go and get it. Okay, so I want to get a little bit boring again. Jonathan, question for you. What systems are used to detect, track, and identify space debris and active satellites?
Okay, I won't take the boring comment personally. Yeah.
That's important. It's going to be fun.
So so there are two ways that you know where satellites are. One is if you're the owner of the satellite, it's working, you're transmitting signals, you pick up the signals, and you can determine its orbit from that. But if it's someone else's satellite, or it's a dead satellite or a piece of debris, you have to use passive means to get at it. You bounce radar energy off it if it's in low orbit, or you spot it with a telescope if it's in high orbit. And so the traditional, the longest running way of doing that is the United States Space Surveillance Network that is operated by the 18th Space Control Squadron of the Space Force. And they are the standard source of tracking information. The Russians have their own system. Europe has sort of an experimental system that isn't really prime time yet. And the hobbyists with binoculars fill in the gaps in the public US system by spotting the secret US satellites that are going overhead that are bright enough you can see them with the naked eye. And so all of that information is available on the internet, And so you can fuse it all together and have a pretty good picture of what there is in orbit at a given time.
I have a feeling that what you're describing is a lot harder than it sounds, and that's a whole nother discussion. We have a few minutes left. I actually want to give you all about a minute each if you want to make any closing comments, or if there's any big takeaways you want the audience to have from this discussion. Like, Lisa, I need like 3 big things that you think we should all remember as we go on to thinking about this issue.
Oh, am I going first?
Yeah.
Okay, I can go first. Let's see, 3 big takeaways.
Or one.
Well, as an environmental historian, I'm always going to be the one, I'm always going to try to point out that when the kind of, and I'm sure that the other 2 panelists agree with me on this, this is more kind of a general comment, that when, that in most issues of environmental crisis, the kind of clear pat response of a particular group of humans comes in and crisis ensues is usually too simple an answer. That there's often a much longer history of engagement with a particular environment, of different ways of engaging with different communities, just a much longer, more nuanced history that can lead to a current status quo. So I would say that my main takeaway would be to consider not just the kind of the usual actors and not the kind of assumption that this was a very cut and dry example of environmental crisis caused by a particular group of people at a particular group of time, but instead broaden the scope to look at this as a truly a global issue, one in which some voices have been privileged over others, and one in which the non-human natural world also plays a critical role. And since Bhavya asked that I plug my book, a lot of this will be covered in more detail in a book that is currently tentatively titled Space Junk, A History of Waste in Orbit, that is under contract with Harvard University Press, publication date TBD.
Thank you. Thank you. We have to get it. Jonathan, your final words.
Yeah, I have a couple points. One is that I really want to push the idea of a holistic view of space environmentalism. Let's not just talk about space debris, let's talk about planetary protection, let's talk about how we're affecting the Earth's atmosphere, upper atmosphere, all in one big lump of space as an environment, and we need to understand and be activist about how we are changing that environment and protecting it and managing it. My other thought is that, my slide showed things are changing fast, much faster than the speed of regulation is right now. We need to act now. I think some short-term things would be put kind of black box RFID tags on commodity RFID tags on all the little CubeSats, so we can at least know which, make it easier when you launch 100 at a time to figure out which is which. It's been over a week, I think, since the Transporter 2 launch, 88 satellites, none of which are have been cataloged yet. And then, mandate things like drag sails for CubeSats in low orbit and other sort of cheap options. Gabriel was talking about the difficulty of getting propulsion on these small satellites, but there are technological options that are being tested now. Now let's mandate them and deploy them.
Thank you, Jonathan. Gabriel, you got the caboose.
Oh, man. Well, I'll try to pull it all together a little bit. I've mentioned before that what we're seeing in space debris is an example of a collective action problem, right? It's a classic collective action problem, just like you see with climate, just like we saw with the ozone layer, just like we see with a whole range of other human activities. It's really easy when you're faced with a collective action problem to either complain about the problem and not fix it, or to sort of throw up your hands and say, this is how humans are. And it is how humans are, right? Humans, whether they're individuals or companies or countries, they're going to maximize their benefit in the short and medium term if the externalities that they're generating, the costs they're imposing on the rest of the world, are not reimposed on them. Okay, that's just sort of how humans are. The way you fix that is by collaboration. There is no other way. There's no other way to get out of that trap of sort of short to medium term thinking with long-term consequences. The only way out of that is to work together, whether that means industry groups working together, whether it means countries working together, whether it means universities coming up with standards for their small satellites, and then building all these things together. It has to be a collective solution because it's a collective problem. And that's the only way you escape from the logic of short-term thinking. So no matter what good ideas individuals or companies or countries might come up with, the only way we're going to solve this is by bringing them all together. So I'll stop there.
Thank you, Gabriel. Those are words to live by. Well, it's 6 p.m. I want to thank this amazing group of panelists. Thank you so much. This session is going to be on YouTube and other places, so hopefully you all will have a chance to look at it again. I for sure will be watching. I want to thank the NASA History Office and the Smithsonian Air and Space Museum for co-hosting this forum. A really big thank you to Catherine Baldwin for doing all the social media and the audiovisual. And I hope you will come join us for downstream sessions of the Space Policy and History Forum. Upcoming topics include space, nuclear power, and propulsion, among others. So thanks again for joining us. And thanks again, Gabriel, Lisa, Ruth, and Jonathan. Bye, everyone.
Bye, everyone.
Thanks for having me.